Hello students, myself Priyanka Goswami. Today we will study the chapter Converter and Inverter of the subject Power Electronics and Drives. Single phase fully controlled half-wave converter with resistive load. Here, a single phase half-wave controlled rectifier circuit consists a thyristor and an AC voltage source and a load. Load may be purely resistive, inductive or combination of resistance and inductance, but here we will consider a resistive load. Here V0 equals to load output voltage, I0 equals to load current and Vt equals to voltage across the thyristor T. Here T is fired at an angle alpha, which is called firing angle. Now thyristor is forward biased for the positive half cycle of supply voltage. Now load voltage is 0 till SCR is fired. At an angle alpha, SCR starts conducting. But as soon as the supply voltage becomes 0 at omega t equals to pi, the load current will become 0 after omega t equals to pi, and then SCR is reverse bias. Thus thyristor will turn off at omega t equals to pi and remain in off condition till it is fired at omega t equals to 2 pi plus alpha. Now output voltage V0 equals to Vm sin omega t for alpha to pi, and I0 equals to Vm sin omega t by R for alpha less than equals to omega t less than equals to pi. Now we calculate the average value of output voltage. The average value of load output voltage equals to 1 by 2 pi integration 0 to 2 pi Vm sin omega t d omega t. Since the value of load voltage is 0 from 0 to alpha and pi to 2 pi, therefore we can write 1 by 2 pi integration alpha to pi Vm sin omega t d omega t. After solving the integration, we can write Vm by 2 pi 1 plus cos alpha. So for single phase half wave control rectifier, average value of load output voltage equals to Vm by 2 pi 1 plus cos alpha. Now we will study single phase fully controlled half wave converter with RA load. Here this circuit consists an AC voltage Vs equals to Vm sin omega t, a thyristor T and RA load. And we consider output voltage V0 and output current I0. Now we assume that thyristor T is fired at an angle omega t equals to alpha. As soon as the thyristor T is fired at omega t equals to alpha, load voltage is equals to the source voltage instantaneously appears across the load terminal because the thyristor is forward biased in between 0 to alpha. So once thyristor is gated, it starts conducting. But the current does not start at this instant of firing because of the nature of load. Since the load is inductive, that is why it will not allow any sudden change in the circuit. Therefore, omega t equals to alpha, the output current will be 0 and it will gradually increase. The output current will become maximum and then starts decreasing. The behavior of load current will not be observed for purely resistive load. But at omega t equals to pi, load voltage V0 reduces to 0. So the load current will not be 0 at this instant because of the inductance. So thyristor will not turn off even it is reverse biased. After omega t equals to beta, V0 equals to 0 and I0 equals to 0 at omega t equals to 2 pi plus alpha. And the SCR is triggered again. Output voltage is applied to the load and the load current develops as discussed before. Now the angle beta where the load current becomes 0, that is called extension angle, and the angle beta minus alpha for which SCR is on, that is called conduction angle. Now steady state load current for single phase half wave control rectifier is given. Here output current equals to Vm by root over r square plus omega L square sin omega t minus phi, where phi angle equals to tan inverse omega L by r. Here phi, what is phi? Phi is the angle by which RMS current lags behind the RMS voltage. For 0 to alpha and beta to 2 pi, the value of load voltage is 0. Therefore, average output voltage equals to 1 by 2 pi alpha to beta Vm sin omega t d omega t. And after solving this equation, we get Vm by 2 pi cos alpha minus cos beta. Now, single phase fully controlled full wave converter with R load or with resistive load. Figure shows the single phase full wave control rectifier with R load. Here, this is used mainly speed control of DC motors, battery charging, and front end of UPS or SMPS. And this single phase fully controlled rectifier converts single phase AC into DC. Here, 4 thyristors are used. And turn on instance of these devices or thyristors are depend on the firing angle. In positive half cycle of the thyristor T1 and T2 are fired at an angle alpha. When T1, T2 conducts, output voltage equals to source voltage, and also so output current equals to source current, that is equals to output voltage by R or source voltage by R, because V0 equals to Vs. And in case of negative half cycle of input voltage, thyristor T3 and T4 are triggered at an angle pi plus alpha. So here the output current equals to minus Is. So Is equals to minus I0. And T3 and T4 becomes off at an angle 2 pi. Now we will study single phase fully controlled full wave converter with RL load. Figure shows the single phase full wave controlled rectifier with RL load. Now there are 4 modes of operation. First, mode 1, alpha to pi. In this mode, the positive half cycle is applied to AC signal. Thyristor T1 and T2 are forward biased and it turned on at an angle alpha. Now load voltage is equals to positive instantaneous AC supply voltage or load voltage equals to source voltage. The load current is positive, ripple free and constant, and that is equals to I0. Now mode 2, pi to pi plus alpha. At omega t equals to pi, input supply equals to 0, and after pi it becomes negative, but because of the inductance it opposes any change through the circuit. So to maintain a constant load current and also in same direction, due to this induced voltage, thyristor T1 and T2 are forward biased. The load voltage is negative and it is equals to instantaneous AC supply voltage or AC supply voltage, while load current is positive. So here load acts as a source and stored energy in inductance is returned back to the AC supply. Now mode 3, pi plus alpha to 2 pi. At omega t equals to pi plus alpha, T3 and T4 are turned on and T1 and T2 are reverse biased. Load voltage again becomes positive and energy is again stored in the inductor. So T3 and T4 conduct a negative half cycle from pi plus alpha to 2 pi. With positive load voltage and load current energy gets stored. Now mode 4, 2 pi to 2 pi plus alpha. At omega t equals to 2 pi, input voltage passes through 0. So inductive load will try to oppose any change in current and it maintain load current constant and in the same direction. Induced EMF is positive and T3 and T4 with reverse polarity. So VL is negative and it is equals to supply voltage, where load current continues to be positive. Thus, also, load acts as a source and stored energy in inductance is returned back to the AC supply. And at omega equals to alpha or 2 pi plus alpha, T3, T4 are commutated and T1, T2 are turned on. In this slide, we will study three-phase fully controlled bridge converter with RL load. Now, three-phase fully controlled bridge rectifier can be constructed using 6 thyristor, as shown in the figure. The three-phase bridge rectifier circuit has 3 legs, each phase connected to one of the 3 phase voltages. It can be seen that the bridge circuit has 2 halves, positive half and negative half. Positive half consists SCR, S1, S3 and S5, and the negative half consists S2, S4 and S6. At any time when there is current flow, one thyristor from each half conducts. So now the phase sequence be RYB and SCR triggered in the sequence S1, S2, S3, S4, S5, S6 and S1 and so on. Now the operation of the circuit is first explained with the assumption of diodes in the place of thyristor. Here, three-phase voltages can be defined. VR equals to E sin theta, Vy equals to E sin theta minus 120 degree, and Vb equals to E sin theta plus 120 degree. And also in the table, period, range of Q and thyristor pair in conduction. So now it can be seen that R phase voltage is the highest of the three phase voltages when Q is in the range from 30 degree to 150 degree. It can be also seen that Y phase voltages is the highest of the three phase voltage where Q is in the range from 150 to 270 degree and B phase voltage is the highest of the three phase voltages when Q is in the range from 270 degree to 390 degree or 30 degree in the next cycle. We also find the R phase voltages is the lowest of the three phase voltages where Q is in the range from 210 to 330 degree and Y phase voltage is the lowest of the three phase voltage when Q is in the range from 330 degree to 450 degree or 90 degree in the next cycle. And B phase voltage is the lowest when Q is in the range from 90 degree to 210 degree. So the positive rail of the output voltage of the bridge is connected to the topmost segment of the envelope of the three phase voltages and the negative rail of the output voltage to the lowest segments of the envelope. Thank you.